Hi and Assalamualaikum. My name is Edia Adila binti Nasaruddin, matrix number E190074. So I'll be explaining the 3.0, which is introduction. So for this project, as universe facts that people around the world know is DC motors are commonly used in numerous industrial applications like servo system and speed control application. For such system, more commonly known as PID controller is usually the controller of choice due to its ease of implementation, ruggedness and easy tuning. Some of the industry applications which are worth mentioning in which DC motors are being used widely are machine tools, paper mills, textile industry, electric traction and robotics. This because PID controller is ease of control, low cost maintenance of brushless DC motor type and low price. So in this report, we will explain about the control system theory, techniques and concept based on research and facts that we got. And also we solve the control system problem to derive the mathematical model of the system and also draw the block diagram of the system. In addition, we will analyze every result in detail from MATLAB software. So the objective of this project is to explain and solve control system engineering problem using control system theory, techniques and concept. And we also to use and incorporate engineering tools to solve a control system problem, which is MATLAB. And we also objective to demonstrate the importance of classical and modern control system in current technology for sustainable development.
Hi, Assalamualaikum warahmatullahi wabarakatuh. My name is Amrita binti Omar and I will be explaining to you why we are doing this project. So basically, DC motor is one of the electrical machinery that converts electrical source to mechanical source. They can be controlled in high variable and wide range since they are very flexible and high stability. But we need DC motors to have a speed control. So we are going to design a speed control system for the DC motors. Speed control system is a system that allows you to adjust the speed either increasing or decreasing the speed freely. So this is a DC motor. So we are going to apply a speed control system to the DC motor. This part of controlling a motor is very important since even the smallest change on the speed of the DC motor can lead to the non-stability of the closed loop system. So we are going to present our project by using MATLAB Simulink. So we are going to simulate the PID controller in MATLAB and have settling time less than 2 seconds and a step response with overshoot less than 5%. So here is the PID controller that is connected to the DC motor. So we are going to proceed with the project by using the desired requirement. So the design requirement needs to have a VA, rated system terminal voltage by 12 volt, JM, moment of inertia of the rotor is 0.222 kg meter per square, JL, moment of inertia of 0.022 kg meter square, motor friction is 0.003 nms per second, and the viscous friction by 0.005 Newton meter per second, and electromotive force is 1.25 volt per second per rad, and the motor torque constant is 1.28 Newton per ampere. Electric resistance is 11.2 ohm. Electric inductance is 0.12 Henry, and rated system speed is 2000 RPM. So this is the Simulink model of the DC motor speed control with PID controller that we simulate in the MATLAB. And then the equation that we use is 1.28 over 0.0295 seconds cube plus 2.7332 s squared plus 1.6392 s.
Assalamualaikum, my name is Nur Akila and I'll continue on the problem elaboration. So, PID controller is most widely used, which it's involved in proportional, integral and differential parts. The majority of the programmable logic control, PLC, handles a range of practice with this structure. For instance, PID control is broadly used in many fields. The closed-loop cycling experiment and the step-response curve experiment, which run their tests around the nominal operating point, are two PID controller procedures that are most well-known than others. We have the auto-tuning and the manual tuning.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nurhidayah Najwa binti Sharlin and my metric number is AE190039. And this is part D, which is determine PID gain manually. So first we need to do the mathematical modeling of system. First one is the armature circuit equation, and then first equation applied to the motor, relationship between torque and armature current, relationship between motor, EMF, and motor shaft velocity, And then from equation 3 and 2, we will get the new equation, which is for the current. And then we insert equation number 4 and equation number 5 into equation number 1, and then we get this new equation. And then we assume that ZA is equal to this, and after we do the equation, we simplify the equation, we will get the final transfer equation as this one. And then for the total of moment of inertia and viscous friction, we get Zt equal to 0.244 kgm squared and Bt equal to 0.0035 nms per radian. Then after that, we insert all the value inside the transfer function that we already find before, and then this is the new transfer function, which is 1.28 over 0.0295 s3 plus 2.7332 s squared plus 1.6392 s. Then we will need to do the stability analysis test, which is the Root-Hurwitz stability criterion. So the system has a transfer function of this one, 1.28 over 0.0295 s3 plus 2.7332 s2 plus 1.6392 s. Then the transfer function obtained after resetting is as follow, which we have 1.28 kp plus 1.28 kp over 0.0295 s3 plus 2.7332 s squared plus 1.6392 s plus 1.28 kp. Then from the transfer function, this one, we get the characteristic equation as follow, which is the Rs is equal to this equation. In this table 1.1. And then after we calculate for the coefficient A1, we get Kp is 118.5265, and then K is 1.28 times 118.5265, we get 151.7139. And then for B1 is equal to K, so after that we get Kp is 0. So from the findings, the range of Kp is between 0 and 118.5265. Then we do the Ziegler-Nichols second method of tuning rule. After examining the coefficients of the first column of root table, we find that sustained oscillation will occur if Kp is equal to 118.5265. Then the critical gain, KCR, is equal to 118.5265. Then with gain Kp is set equal to 30, the second order characteristic equation becomes 2.7322 S2 plus 118.5265 equal to 0. Then in order to find the frequency of the sustained oscillation, we substitute the S in this equation into J omega, and then we get the new equation as here. And then we find the frequency. So the frequency of the sustained oscillation is omega squared equal to 43.3813, or omega equal to square root 43.3813. So then the period of sustained oscillation is 2 pi over omega, which equal to 0.9540. So this is the table of PID controller gain for manual tuning. So for the P-type controller, the Kp is equal to 59.2633. For PI controller, the Kp is equal to 53.3369. Ti is 0.7950. Ki is 67.0904. And then for PID controller, the Kp is 71.1159 and Ti is 0.4770. And then Ki is 149.089. And then Td is 0.1193 and Kd is 8.4841. And I'm going to explain about part E and part F. Create the control system block diagram for manual tuning PID controller on MATLAB Simulink, and then attach this block diagram on the report. So this figure shows the block diagram for PID controller. Here we have input speed, sum, gain for Kp, Ki and Kd, and then we have integrator and derivative, another sum, transfer function block, and scope. And this is marked. Next is F. Implement P, Pi and PID controller using PID gain from table 1, system without controller open loop, and plot the response of each controller versus input signal, which the input signal is 900 RPM and 1500 RPM. So the first one is the P controller. This is the block diagram of P controller, which we have input speed, sum, gain for Kp, transfer function, marks, and scope. So this is the P controller response versus input speed, which is 900 RPM graph. The magenta is representing the input speed and the blue color is representing transfer function. This is the P controller response versus input speed, which is 1500 RPM graph. So figure 1.2 shows P controller block diagram with Kp equal to 59.2633. There are two input speed to be set, which are 900 RPM and 1500 RPM. Figure 1.3 and 1.4 shows the controller output response versus input speed graph for each input speed. The P value for transfer functions and with response are different for each speed, which is 1700 for 900 RPM and approximately 2900 for 1500 RPM, while the step response for input speed each represent 900 RPM and 1500 RPM, and the transfer function sine wave response peak starts to decrease as time increase. So the peak started to decrease as the time increased, same as this one. Next is the PI controller. This is the PI controller plot diagram, which we have input speed, sum, gain, KP, KI, integrator, sum, transfer function, max, and scope. So this is the PI controller response versus input speed for 900 RPM graph. And this is the PI controller response versus input speed for 1500 RPM graph. So figure 1.5 shows PI controller block diagram with KP equal to 53.3369 and KI equal to 67.0904 with input speed set to 900 RPM and 1500 RPM. Figure 1.6 and 1.7 shows the controller output response versus input speed graph. For transfer function response, the peak started to increase following the time. The highest peak of the transfer function wave for 900 RPM is estimated around 3 times 10 to the power of 4, and for 1500 RPM is approximately 5 times 10 to the power of 4. Next is the PID controller. So this is the block diagram for PID controller. We have 3 gain here, which is KP, KI, and KD. And then we have integrator and derivative. So this is the PID controller response versus input speed for 900 RPM graph. And this one is for 1500 RPM graph. So figure 1.8 shows PID controller block diagram with KP equal to 71.1159, KI equal to 149.0899, and KD equal to 8.4841. Figure 1.9 and figure 2.0 shows the controller output response versus input speed graph for 900 RPM and 1500 RPM. The transfer function sine wave peak for both speeds started to decrease and became constant as time increased. For 900 RPM, the peak for transfer function sine wave is approximately 1500 and started to decrease and become constant, while for 1500 RPM, the peak is more than 2500 and started to decrease and become constant. As the sine wave became constant, the value is equal to the respective input speed value. Next is without the controller. This is the block diagram without controller system. And this is the graph for without controller response versus input speed for 900 RPM, and this one is for 1500 RPM. So figure 2.1 shows a without controller or open loop system block diagram, while figure 2.2 and figure 2.3 shows the controller output response versus input speed graph for each speed, which are 900 RPM and 1500 RPM. Each transfer function response value are different, which for 900 RPM is more than 5000, while for 1500 RPM is around 8000 until 900.
Next, I will presenting the part of H, develop table for comparing the PID controller gain from manual and automatic tuning, which is in table 2. So basically, we have this block diagram. This is the manual PID controller, and this is the automatic PID controller. So in this table 2, we have a manual and automatic value for PID controller. So we have PID turning, which is for manual and automatic. For the manual, we have KP is 71.1159, and for the KI of manual, we got 149.0899, and for the KD for manual, we got 8.4841, and for the automatic, we got KP is 1.7315, and for the automatic KI, we got 2.0779, and last one is for the KD for automatic, we got negative 0.0778. So basically, for the manual PID turning, we got from the manual calculation, and for the automatic, we got from the simulation of MATLAB. Okay, next, for the part I, plot comparison to PID controller responses, input versus manual versus automatic turning. And we need to make sure the PID controller is built to minimize maximum overshot. Overshot percent is less than 10%, and rise time, settling time, peak time, and error condition stable from the system responding without controller, then complete table 3. Okay, so right here we have automatic turning of PID controller. So this is the scope of step block. We have time second versus amplitude. So basically this is the scope for automatic turning of PID controller. So right here we also have the parameters. We have PID and we have performance of robustness. Okay, so right here we have get the value of rise time, settling time, overshot, and peak. Okay, so basically this automatic turning signal responses of PID controller with 1500 RPM. And then next we have this figure 4, which is manual turning signal responses of PID controller with 1500 RPM. So this is the scope. We have the information here, and then this is the PID controller responses, which is input versus manual versus automatic turning, okay, with 1500 RPM. So right here, if we can see, we have three line here, which is blue line, purple line, and yellow line or green line. Okay, so for the purple blue line is for the manual, and for the purple line is for automatic, and this is for the green is speed. Okay, and also here we have the information that like overshot, cycling time, rest time. Okay, alright. So we need to fill up the table 3, which is comparison between manual and automatic of PID controller. So here we have PID turning for manual and automatic. So here we have overshot, TP, TR, TS, and ESS. So for the overshot, we got for manual is 71.55%, and for the automatic is 10.2%. Okay, for the TP is time peak. So we got for manual is 1.57 second, and for the automatic is 1.10 second. And for the TR, we got for manual is 1.94 second, and for the automatic is 1.20 second. And for the TS is cycling times, we got for manual is 5.66 second, and for the automatic is 13.4 second. And for the ESS, we got the result that both manual and automatic is stable. So thank you.